We discussed the general setup, the philosophy behind hypothesis testing. Now let's visit some of the details on how to implement a hypothesis test for a test for the population mean of a single population. Recall from our discussion of confidence intervals for a population mean that we could encounter two situations. One where sigma, the standard deviation of the population, is known, and the other where sigma is not known. We said that it would be rare that sigma would be known, that we wouldn't know the population mean, but we would somehow know the dispersion of the population. However, let's first discuss the case where sigma is known for pedagogical purposes, as it makes for an easy transition into hypothesis testing. Also, like our discussion of confidence intervals, when sigma is known, there are three cases that we may encounter. The first case is where the population is known to be normally distributed and the sample size is small. The second case is where we don't know anything about the population distribution, but we collect a sufficiently large sample size such that the central limit theorem kicks in. In either of those two cases, we use the z-distribution to identify the rejection region, and the test statistic is a z-score. In the third case, when the population distribution is non-normal and when the sample size is small, that is, we don't think the central limit theorem will help us, we use non-parametric techniques that we'll discuss in a later unit. Say we've got a set of hypotheses about a population mean. The null hypothesis is that the mean is equal to mu naught, and the alternative hypothesis is that the mean is not equal to mu naught. This is a two-tailed test, as we have strict equality in the null and strict inequality in the alternative. We want to reject the null if the evidence lies significantly above or significantly below the mean. Therefore, the rejection region of the size alpha is dispersed in both tails. And recall that we said that the test statistic essentially represents our evidence. So what is the test statistic? When we are testing about a population mean, when sigma is known, the test statistic is a z-score. Test statistic z0 or z0 is measured as the difference between y bar and mu naught in the numerator and sigma over root n in the denominator. That is, how different is y bar from the hypothesized mean in standard deviation units. Remember, a z-score represents how different a realization of a random variable is from the mean of the distribution in standard deviation units. That's what we're using here. How different is our sample evidence from the hypothesized value in standard deviation units? If y bar is far enough from mu naught, the test statistic will lie in the rejection region. How cool is that? We're taking the notion of a z-score and applying it to a measure of the distance from the sample to the hypothesized value. So we're accounting for variability in sample size here with the denominator, sigma over root n. Recall that sigma over root n is the standard deviation of the sampling distribution of y bar. We're explicitly accounting for variability in sample size when we're determining how far apart the sample mean is from mu naught. And confidence comes into play with the size of the rejection region. So we're considering variability, sample size, and confidence when we draw a conclusion about a hypothesis. Remember, we can't just make a decision about a hypothesis based on y bar alone. It's a random variable. We need to account for how dispersed the data are. If the data are really dispersed, y bar could be quite a bit different from mu naught, and we might still be convinced that the mean is indeed mu naught. That is, the higher the variability, the more possibilities there are for y bar to take on values that are different from mu naught. Putting sigma over root n in the denominator helps us account for this variability. Also, the larger the n, the better we feel that y bar is representing the real mean of the population. So if y bar is really different from mu naught, maybe mu naught isn't the real mean and we should be rejecting the null. So, to recap, if the test statistic lies beyond the critical value, that is, if the test statistic lies in the rejection region, then we can conclude that the sample mean lies too far from the hypothesized mean for the two to be equal. Therefore, we reject the null hypothesis. Here, too far is defined by our confidence. If the test statistic doesn't lie in the rejection region, then we conclude that we do not reject the null hypothesis based on the evidence. Note that we never say, accept the null. The best that we can do is fail to reject the null. It's a pessimistic perspective, but there's too much variability in sampling for us to use the language like, accept the null. So how do we determine if the test statistic lies in the rejection region? There are two approaches that we can use to draw a conclusion about a set of hypotheses: the critical value approach and the p-value approach. We'll discuss both of these in upcoming videos.